Okay, so we're going to start talking about piecewise functions today. And so what I've got in front of you here is a piecewise function made of three different pieces. So we have our f function right here, and we see our big huge bracket, which means we're going to take three different types of functions and put together to make a big function. And so you'll notice that our first type of function we have here is the absolute value function. Then we have a square root function. Then we have a linear function. So we're going to take these three pieces of a function and put together to make a big piecewise function. And so you'll notice a bunch of colors on my example here. So you're actually going to do a lot of coloring to get used to graphing these piecewise functions. We're going to see something very important here is our domain. So like this red function, this absolute value function, which I have circled in red, only exists with this piece from -9 to -1. So that's my domain. So over here on my graph, you see I have colored. See, here's my origin right here. And I have colored in from -1 to -9 on my function, on my graph. I've colored all that in red because in this red section is where I'm going to see my absolute value graph. And so I know, based upon our transformations already, that this absolute value graph is going to be concave down. It's going to shift left 4 and up 5. And so I can use that information to know exactly where to plot my points. So for this absolute value function, we just said my vertex was -4, 5. So I'm going to go ahead and plot that. So here's my origin again. Don't get confused with your colors here. So -1, 2, 3, 4, and then up 1, 2, 3, 4, 5. So this is my vertex of my absolute value function. And so it's going to be on my table, -4, 5. And so with piecewise functions, we've got to understand that they're giving us our domain. So they're telling us that I want to graph this function from x is -9 all the way to when x is -1. So on my table, I didn't leave enough room here, but I have to use those points. Okay? And I have to use all the way to -1. Now the issue here is to understand, when I'm going to have points and when I'm going to have holes, and that takes us back to algebra 2. Remember that if you have just the inequality symbol, then that's going to be just a hole. But if I have the equal sign, so if I'm including that number, then I have a point. So basically, I'm really concerned with the endpoints of this graph. I know I'm going to have a V. I know it's going to be concave down. I see that. I understand that. But I have to take care of the endpoints. So my big concern here is plugging in this -9. And I apologize for my table not being big enough. I guess I could fix it here. Okay. So if I plug in my -9, and we can do our work here. -9 plus 4 is -5. Absolute value of -5 is 5. Negate it, or times it by a negative, makes it -5. And then plus a 5, I'm going to get 0. So my ordered pair, -9, 0. So I know all the way over here, I'm going to be at there. Now, I've already made a mistake. As soon as I plot that point, I see my mistake. Because my x is greater than -9. There's no equal to sign here. And that means that this point should actually have been a hole. So when I go to plot this, I want to plot a hole. It's very important with piecewise functions. You've got to make sure you understand your points and your holes. There's a big difference here. Okay? So when I go to plug in -8, -8 plus 4 is -4. Absolute value of a negative number is a +4, but I'm going to times it by a negative, so it's -4 plus 5, we get a 1. And so I have the ordered pair at -8, 1. And we can see our pattern. We know exactly what our V is going to look like. So we should already be able to figure out all these numbers by plugging in. Okay? I'm going to go ahead and plug these numbers in. I'm going to pause the video and do that because I think you can do that as well. Then I'm going to come right back. Okay, so I went ahead and plugged in all my numbers, and I've gotten all my points. But again, you need to recognize here that everything here is a point. Every single one of these are points. The only one that was a hole was this very last one in my domain, which says that x is just greater than -9. So there's no point there. It's just only going to be a hole there. Then I know I'm going to take my other side, And we can look at our pattern and we know what the graph's going to look like. But we're really concerned here. We know our pattern's going to be like this. We're really concerned about this last number here. Okay? Now, we know my pattern. Let's double check and make sure it works. I'm going to plug in -3. -3 plus 4 is 1. Absolute value of 1 is 1. Times by negative is -1 plus 5. So that's how I got my 4. So I got -3, 4. I'm right. Okay? Plugging in -2. You can do it in your head real quick. You're going to get a 3. I agree with that. We're going to plug in -1. So if I plug in -1, -1 plus 4 is 3. Absolute value of 3 is 3. Times by negative is -3 plus the 5. So I get 2. So I've got the point -1, 2. The question here is that point going to be a point or a whole? So if I look at my inequality symbol, I have less than or equal to. That means I include, so that means right here I'm going to have a point. So right there is a point. So you're going to notice on this graph, there's my absolute value piece. Starts off with a whole on my -9 and a point right here on -1. Okay? We're going to do the exact same thing now, but do it in the middle on our yellow section. Our yellow section is a square root graph. We're only going to have the square root graph on this domain of -1 to 3. So I know on my table here, I'm going to try to plug in numbers between -1 and 3. Okay? So if I look at -1, -1 plus 1 is 0. Square root of 0 is 0. Times by negative still 0. Minus 2. So I'm going to get -1 minus 2. Look at your notation. That's one of my endpoints. By looking at this symbol, I know it should be a whole because it's not equal to, so it's going to be a whole. So when I plot -1, -2, I'm going to clearly make sure you can tell that's a whole down here. Okay. I want to see if I can use a 0. 0 plus 1 is 1. Square root of 1 is 1. Times by negative is -1. Minus 2, so I'm going to get -3. Remember, everything in between is always points. We only test our endpoints to see if they're wholes or not. So I've got 0, -3. Looks down here. That one's going to be a point. I'll plug in a 1. May not be able to use it, but we'll see. 1 plus 1 is 2. Square root of 2 is a decimal. I don't want to use that one, so I don't even have to acknowledge that one exists. Okay? I skipped on my table. I skipped 2, but we'll try it anyway. So 1 plus 2 is 3. Square root of 3, I don't know it. Now I didn't want to use it anyway. That's why I skipped it, I'm sure. Let's try 3. 3 plus 1 is 4. Square root of 4 is 2. Times by a negative, so -2. Minus 2. So I get -4. So I've got the ordered pair 3, -4. But again, look at your inequality. This time it's going to be a whole. It's a whole again because there's no equal to sign. So I've got the point 3, -4. There's a whole. So my square root function, the only piece I want, looks like that. Now, let's make sure we understand that. According to what we already know from transformations, this is a square root function that reflects across the x-axis. It did. Shifted left 1. It did. And down 2. It did. This has no arrows on either side because my domain was just between -1 and 3. So I don't want any numbers at all except for these numbers in between. Same thing with my absolute value function. There's no arrows here because I just want the numbers in between -9 and 1. Okay? Well, my last function, my purple function, is linear. So it's going to be a line. But look at its domain. I want a line for every number greater than 3. So I want a line.
Excuse the interruption at this time.
Okay, I apologize for that. Had to pause for announcements. Now I'm back. So I want this linear function, but I want this linear function to cover this entire purple section. And actually it says I want it to cover everything greater than 3. So if this graph kept going, I would have to color in all of this entire side as far as it would go purple, because that's how I want my graph to go. I want it to go on forever and ever for every number bigger than 3. So when I make my table, I'm going to start with 3, okay, and then plug in 3, I know it has a fraction, but we can get used to fractions. 1/3 of 3. So negative 1/3 times 3 would give me a negative 1, minus 3 would give me a negative 4. So I have the ordered pair 3, negative 4, and then look at your symbol. There's no equal to there, so that means right here I want there to be a whole. So over here on my graph, I'm at 3, negative 4. There's already one there, and make sure there's a whole, so there's the whole. Okay, so actually this yellow section and purple section share this whole right here. Then when I keep going, I want numbers bigger than 3. And if you had a calculator, you can use 4, because you would plug in and you would get negative 1/3 times 4 would be a negative 4/3, and you can subtract a 3 from that. And we can do all that stuff and deal with fractions, but I'd rather not deal with fractions because I'm not giving calculators to my classes. So I want you to think of multiples of 3. Like, next number I think of is 6, because now I want to plug in a 6. Excuse me. I've got negative 1/3 times 6. If you do the math on that, negative 1/3 times 6 is actually a negative 6/3, which is a negative 2. And that minus 3 gives me a negative 5. So I got my next point here at 6, negative 5. And again, remember, everything after that whole becomes a point. I don't want to plug in 7, it's on multiple of 3, 8, no, but 9 is. So I plug in 9. 1/3 of 9, negative 1/3 times 9 is a negative 3. Minus 3 is a negative 6. So I want to plug in, I gotta go back and erase this because I graphed the wrong point. I want 6, negative 5. So over here, 1, 2, 3, 4, 5, 6, negative 5. There it is. Look if that's better. And now I'm at 7, 8, 9, negative 6. And you can tell that my linear function is starting to take shape. You could also graph this by looking at your slope. My slope says for my first point I go down 1, right 3. So from that hole I started off with, down 1, right 3, here's my point, down 1, right 3, here's my point. Okay? So I can see the shape of my linear function. Let's make this linear right here. Looks like that. And if this had been a domain that stopped at 3, then this would be my graph. But this says for every number greater than 3. That goes on for forever and ever and ever and ever. So I have to show that on my graph by continuing my function with an arrow. This will be your graph. So this graph is made up of 3 sections. An absolute value section that's cut off between negative 9 and negative 1. A square root section that's cut off between negative 1 and 3. Then a linear function that lasts from 3 to infinity. And these 3 pieces together create this big, huge piecewise function. Okay? So the only thing we have left to do is, I hate leaving my tables without notation. So make sure in your table, you know this is x and f of x. Or you could say y, but always use notation. So it would look like that. So this is your final product. Okay? This is actually on page 12 of your packet. It's example number 10 if you want to go copy that down. And then we will do the rest of this packet in class together. So these are your notes.